Welcome to the presentation on moments. So just if you were wondering, I have already covered moments. You just may not have recognized it because I covered it in mechanical advantage and torque. But I do realize that when I covered it in mechanical advantage and torque, I think I maybe overcomplicated it. And if anything, I didn't cover some of the most basic moment of force problems that you see in your standard physics class, especially physics classes that aren't focused on calculus or going to make you a mechanical engineer the very next year. So we did that with, why did I write down the word mechanical? Oh yeah, mechanical advantage. That's if you do a search for mechanical advantage, I cover some things on moments and also on torque. So what is moment of force? Well, it essentially is the same thing as torque. It's just another word for it. And it's essentially force times the distance to your axis of rotation. What do I mean by that? Well, let me take a simple example. Let's say that I have a pivot point here. Let's say I have a pivot point here. Let's say I have some type of, some type of seesaw or whatever. There's a seesaw. And let's say that I were to apply some force here, and the forces that we care about, and this was the exact same case with torque because they're essentially the same thing. The forces we care about are the forces that are perpendicular to the distance from our axis of rotation, right? So in this case, if we're here, the distance from our axis of rotation is this. That's our distance from our axis of rotation. So we care about a perpendicular force, either a force going up like that or a force going down like that. So let's say I have a force going up like that. Let's call that F, F1, D1. So essentially, the moment of force created by this force is equal to F1 times D1, or the perpendicular force times the moment arm distance. This is the moment arm distance. Moment arm. That's also often called the lever arm if you're talking about a simple machine, and I think that's the term I used when I did a video on torque. Moment arm. And why is this interesting? Well, first of all, this force times distance, or this moment of force, or this torque, if it has nothing balancing it or no offsetting moment or torque, it's going to cause this seesaw in this example to rotate clockwise, right? This whole thing, since it's pivoting here, is going to rotate clockwise. The only way that it's not going to rotate clockwise is if I have something so right now, this end is going to want to go down like that. And the only way that I can keep it from happening is if I exert some upward force here. So let's say that I exert some upward force here that perfectly counterbalances, that keeps this whole seesaw from rotating. F2, and it is a distance D2 away from our axis of rotation, but it's going in a counterclockwise direction, so it wants to go like that. So the law of moments essentially tells us, and we learned this when we talked about the net torque, it essentially tells us that this force times this distance is equal to this force times this distance. So F1 D1 is equal to F2 D2. Or if you subtract this from both sides, you could get F2 D2 minus F1 D1 is equal to 0. And actually, this is how we dealt with it when we talked about torque. Because just the convention with torque is if we have a counterclockwise rotation, it's positive, and this is a counterclockwise rotation in the example that I've drawn here. And if we have a clockwise rotation, it has a negative torque, and that's just the convention we did, and that's because torque is a pseudo-vector, but I don't want to confuse you right now. What you'll see is that these moment problems are actually quite straightforward. So let's do a couple. It always becomes a lot easier when you do a problem, except when you try to erase things with green. So let's say that, let me plug in real numbers for these values here. Let me erase all of this. Let me erase some of let me just erase everything.